Good evening and welcome back to Plane Crash for Sleep. I'm glad you're here. Wherever you are in the world tonight, I want you to get comfortable, really comfortable. Take your time adjusting your pillows, arranging them just so beneath your head and neck. Pull your blanket up to whatever height feels right, feeling its weight settle over you like a gentle reminder that you're safe, you're here, you're allowed to rest. Dim the lights until they're barely glowing, or turn them off completely if darkness is what you need tonight. Take a deep breath now, slowly, filling your lungs completely, and then let it out even more slowly, feeling the tension drain from your shoulders, from your jaw, from every muscle that's been holding you up all day. We're about to travel together, you and I, back through time to a bright blue afternoon in May of 1979, to the beginning of a holiday weekend in America, to one of the busiest airports in the world, where a routine takeoff, the kind that happens thousands of times every single day, became something no one ever expected it could become. This is the story of American Airlines Flight 191. It's a story about maintenance procedures, about small cracks invisible to the naked eye, growing slowly over weeks and months, about assumptions built into the design of aircraft, about the distance between what we think we know and what we don't know we don't know. It's a story about a maintenance shortcut that saved time and money and seemed perfectly reasonable to everyone involved. A shortcut that would never have caused problems if a dozen other factors hadn't aligned in precisely the wrong way at precisely the wrong moment. It's a story about three highly experienced pilots doing everything right according to their training, following procedures to the letter, making the correct decisions based on the information available to them, and still being unable to prevent disaster because the information they had was incomplete, because the aircraft was hiding a secret that no instrument could reveal, because their training hadn't prepared them for a scenario that had never happened before in the history of commercial aviation. It's a story about the deadliest aviation accident ever to occur on American soil, an accident that would take months to investigate and understand, an accident that would ground an entire fleet of aircraft and shake public confidence in the very idea of flying. An accident that would ultimately make aviation safer for everyone who came after. This is the story of the McDonnell Douglas DC-10's darkest day. A story that begins not on that Friday afternoon in May, but months earlier, in a maintenance hangar in Tulsa, Oklahoma, where mechanics were trying to do their jobs efficiently, where engineers had developed what seemed like a clever procedure to save time, where everyone believed they were doing the right thing. It's a story with 273 victims, 258 passengers, 13 crew members, and 2 people on the ground who happened to be in the wrong place at the most terribly wrong time. It's a story that still haunts Chicago, that changed how airlines maintained their aircraft, that revealed vulnerabilities in aircraft design that no one had considered. So settle in, let your breathing slow and deepen, and let me take you back to that Friday afternoon, to the moments before everything changed. The date is May 25th, 1979, a Friday. The time is approaching 3 o'clock in the afternoon, Central Daylight Time. Though as with all these stories, time will soon take on a different quality, will compress and expand, will contain lifetimes in seconds. For now, though, picture the scene. If you close your eyes, and please do, let them close gently. You can almost see it. The sky over Chicago is a brilliant, cloudless blue, the kind of blue you only see on perfect late spring days,
when winter is truly gone, and summer hasn't yet arrived with its humidity and haze. The temperature hovers around 70 degrees Fahrenheit, pleasant and mild, with a brisk northeasterly breeze that carries with it the sense of Lake Michigan and the promise of the coming weekend. This is Memorial Day weekend, the unofficial start of summer in America, a 3-day holiday when schools are winding down, when families plan trips and barbecues, when millions of people pack their bags and head to airports to visit relatives or explore new places, or simply get away. The mood across the nation is light, optimistic, filled with the simple pleasure of a long weekend ahead. At Chicago O'Hare International Airport, one of the busiest airports in the world, the rhythm of Memorial Day weekend operations is in full swing. O'Hare sits on the northwest side of Chicago, 17 miles from the downtown loop, occupying nearly 8 square miles of what was once farmland, and before that, a manufacturing facility for Douglas C-54 transport planes during World War II. The airport bears the name of Edward Butch O'Hare, a Navy aviator and Medal of Honor recipient who died in combat in 1943. But most travelers who pass through simply know it as O'Hare, 3 letters, O-R-D, that appear on luggage tags and flight information displays around the world. By 1979, O'Hare has firmly established itself as one of the world's most important aviation hubs, handling over 43 million passengers annually, more than any other airport in the United States. The airport sprawls across its territory, with 4 terminals, multiple concourses, and a complex web of runways and taxiways, designed to handle the constant flow of arriving and departing aircraft. On this Friday afternoon, O'Hare is operating at its usual controlled frenzy. Aircraft taxi along the intricate network of taxiways, following yellow center lines painted on the concrete, guided by ground controllers whose voices come through headsets with practiced efficiency. Some aircraft are pushing back from gates, beginning their journey. Others are arriving,
turning off runways onto taxiways, making their way to gates where ground crews wait with jetways and baggage carts and fuel trucks. Still others sit at gates, doors open, being loaded with passengers and bags and cargo and fuel. The main runways, and O'Hare has several, oriented in different directions to accommodate varying wind conditions, see aircraft taking off or landing every 90 seconds during peak periods. It's a ballet of aluminum and jet fuel, orchestrated by air traffic controllers in the tower, who manage this flow with a combination of strict procedures, constant communication, and years of experience. Somewhere on the ramp, being prepared for departure, is a McDonnell Douglas DC-10. Registration number N110AA, American Airlines. The aircraft is pointed toward runway 32 right, one of O'Hare's primary departure runways, a long ribbon of concrete stretching nearly 2 miles, oriented roughly north-south, numbered 32 because its heading is approximately 320 degrees. The DC-10 sits at its gate like a silver giant, its distinctive profile immediately recognizable to anyone familiar with commercial aircraft. 2 engines mounted on pylons beneath the wings, a 3rd engine mounted at the base of the tail, 3 parallel landing gear assemblies visible beneath the fuselage, a swept wing with that characteristic wide-body bulk that speaks of power and range and modernity. This particular DC-10 is a Series 10, the original production version, designed for domestic routes, powered by General Electric CF6 6D engines, producing 40,000 pounds of thrust each. The aircraft was delivered new to American Airlines in February 1972, 7 years and 3 months ago, when the DC-10 was still establishing itself as one of the industry's most advanced aircraft. In those 7 years, N110AA has accumulated more than 20,000 flight hours, flying routes across the American Airlines network, carrying hundreds of thousands of passengers safely to their destinations.
The DC-10 itself represents the pinnacle of early 1970s wide-body jet technology. When McDonnell Douglas launched the DC-10 program in the late 1960s, the company was competing directly with Lockheed's L-1011 TriStar for orders from airlines seeking aircraft that could carry large numbers of passengers on transcontinental and international routes. Both aircraft were tri-jets, using 3 engines instead of the 4 that powered the Boeing 747, and both promised excellent economics and performance. American Airlines was the launch customer for the DC-10, placing an order for 25 aircraft in 1968, betting heavily that this new design would serve them well for decades to come. The first DC-10 entered service in August 1971, and by May 1979, more than 300 DC-10s are flying with airlines around the world, from American and United in the United States to Swissair and KLM in Europe, from Japan Airlines to Varig in Brazil. The aircraft has proven itself capable and reliable in daily
operations, though it has also been the subject of controversy after a catastrophic cargo door failure on a Turkish Airlines DC-10 in March 1974 that killed 346 people near Paris. But on this Friday afternoon at O'Hare, N110AA shows no obvious signs of distress or problems. To the casual observer, to the passengers boarding through the jetway, to the pilots conducting their pre-flight checks, this is simply another DC-10 on another routine flight. The aircraft's exterior is painted in American Airlines' distinctive livery of the era, polished aluminum fuselage reflecting the afternoon sun, a red and blue stripe running along the length of the fuselage, the American Airlines logo on the tail, AA in stylized letters on the forward fuselage. The aircraft looks modern, well-maintained, ready to fly. The passenger stairs and jetway are attached. Ground power is connected. Fuel trucks have finished topping off the tanks, with the thousands of gallons of Jet A fuel needed for the flight to Los Angeles. Catering trucks have delivered meals and drinks for the passengers. Baggage carts cluster near the forward cargo hold as ground crews load suitcases and boxes. Everything proceeds according to the careful choreography of commercial aviation, the system working as it's designed to work. Inside the terminal, 258 passengers are making their way toward Gate K5, where Flight 191 to Los Angeles will depart. This is a diverse cross-section of America. Business travelers in suits carrying briefcases, heading to meetings on the West Coast. Families with children excited about trips to Disneyland. Publishing executives heading to a convention of the American Booksellers Association in Los Angeles. Tourists planning beach vacations. People visiting relatives. The usual mix of humanity that fills commercial flights every day. Among the passengers are notable figures whose names will later appear in newspaper accounts. Sheldon Wax, 51, the managing editor of Playboy magazine, traveling with his wife Judith Wax, 47, an author and columnist, who has written about everything from family life to women's issues. Victoria Chen Hader, 34, Playboy's fiction editor, making her first business trip away from her 1-year-old son. Dozens of other people whose names and stories will be catalogued in the coming days as investigators work to identify everyone aboard. There are children, some as young as 2 years old. There are elderly passengers, retirees traveling to visit family on the West Coast. There are middle-aged professionals, young adults, teenagers traveling alone or with parents. Each one carries hopes and plans, schedules to keep, people waiting for them at the other end of the flight. The crew consists of 13 people, led by 3 pilots and rounded out by 10 flight attendants. In the cockpit, preparing the DC-10 for departure, are 3 highly experienced aviators. Captain Walter H. Lux, age 53, sits in the left seat, the position of command. Lux is one of American Airlines' most experienced DC-10 captains, having flown the type since its introduction to the airline 8 years earlier. He has accumulated approximately 22,000 total flight hours over his career, of which about 3,000 have been in the DC-10. Before joining American Airlines, Lux served as a second lieutenant in the United States Army Air Forces during World War II, learning to fly in the military tradition of that era. He's qualified on multiple aircraft types, the DC-6, DC-7, Boeing 727, and several others, and has spent 3 decades as a professional pilot, earning the respect of his colleagues and the trust of his airline. Lux is filling in on this flight, covering for another captain, a last-minute schedule change that places him in command of Flight 191. He's based in Chicago, knows O'Hare intimately, has conducted the Los Angeles route countless times. This should be, from his perspective, a completely routine flight. In the right seat sits First Officer James R. Dillard, age 49, who will be the pilot flying, the pilot actually manipulating the controls, for this departure. Dillard has accumulated about 9,275 total flight hours, including over 1,000 hours in the DC-10. He's a skilled, experienced aviator, the kind of first officer who makes captains confident, who knows procedures cold, who can be trusted to handle any situation. On this flight, Dillard will make the standard call-outs during takeoff, will advance the throttles, will rotate the aircraft at the appropriate speed, will be at the controls when everything goes wrong. Between and slightly behind the 2 pilots sits the flight engineer, Alfred F. Udovich, age 56, who will manage the DC-10's complex systems during flight. Udovich has approximately 15,000 total flight hours, and about 750 in the DC-10. His station faces sideways, looking at the flight engineer's panel, a wall of switches, gauges, and indicators that monitor fuel, hydraulics, electrical systems, pneumatics, and dozens of other aircraft systems. Udovich is nearing the end of his career, has flown for American for more than 2 decades, has seen the evolution of commercial aviation, from propeller aircraft to jets to wide-body jets. These 3 men represent perhaps 46,000 combined hours of flight experience. They know their aircraft. They know procedures. They trust the machinery around them. The 10 flight attendants include veterans with decades of experience and newer crew members still learning the profession. The senior flight attendant, responsible for managing the cabin crew and ensuring passenger safety, coordinates with the others as they prepare the cabin for departure. They move through their well-practiced routines, checking that overhead bins are closed, that seats are in their upright positions, that tray tables are stowed, that passengers have fastened their seatbelts. They demonstrate the safety features of the DC-10, pointing out emergency exits, showing how oxygen masks deploy, explaining what to do in the unlikely event of an emergency. Most passengers pay minimal attention, having seen these demonstrations dozens of times. But the flight attendants continue through the entire script because regulations require it, and because, though no one knows it yet, some of these procedures will matter in about 30 minutes. The DC-10 is configured for 271 passengers, a mix of first class, business class, and economy class seats spread across the wide cabin. With 258 passengers boarded, the flight is relatively full but not at capacity, typical for a Friday afternoon departure at the start of a holiday weekend. The passengers settle in,
Stowing bags, claiming armrests, buckling seatbelts, opening magazines or books, some already dozing before the flight even begins. The cabin has that particular atmosphere of expectation that fills aircraft before departure. A mix of excitement and routine, of anticipation and boredom, of travelers mentally preparing for the next few hours. Children fidget, adults check their watches, flight attendants move up and down the aisles, handling last-minute requests. Outside the windows, passengers can see ground crews working, can see other aircraft taxiing past, can see the sprawl of O'Hare stretching in every direction. Everything appears normal, safe, routine. No one has any reason to worry. The DC-10 is one of the world's most advanced aircraft. American Airlines is one of the world's most respected airlines. The crew is experienced and professional. The weather is perfect. What could go wrong? But deep inside the aircraft structure, hidden from view, invisible to any inspection that doesn't involve disassembling major components, a crack exists. The crack is in the left engine pylon, the structural assembly that attaches the left engine to the left wing. Specifically, the crack runs through a critical component called the aft bulkhead, a piece of metal that carries enormous loads, that transfers the engine's thrust and weight to the wing structure. The crack is about 25 centimeters long, running through a flange that should be solid, compromising the structural integrity of the entire pylon attachment. The crack formed 8 weeks ago, in March 1979, when N110AA was in a maintenance hangar in Tulsa, Oklahoma, undergoing scheduled maintenance that included replacement of bearings in the engine pylons. During that maintenance, mechanics used a procedure that seemed perfectly reasonable, that had been developed by American Airlines' own engineering department, that had been used successfully multiple times before. But this time, something went slightly wrong. A forklift supporting the engine and pylon assembly shifted fractionally, bringing the pylon's aft bulkhead into contact with a clevis on the wing, applying loads the structure was never designed to carry. The contact created the crack, but the crack was so small, so perfectly positioned, that post-maintenance inspections didn't detect it. The crack was internal, hidden, not visible from the outside. Over the following 8 weeks, as N110AA flew routes across American Airlines' network, the crack grew. Every time the engines throttled up for takeoff, every time the aircraft hit turbulence, every time loads passed through the pylon structure, the crack propagated a little further. Metal fatigue, the phenomenon where repeated stress cycles cause cracks to grow, even when the stress levels are well below what would cause immediate failure, worked its patient, invisible damage. By May 25th, the crack has grown to about 33 centimeters, 13 inches, running through a critical section of the bulkhead. The pylon is now held to the wing by a rapidly diminishing amount of intact metal. One more stress cycle, one more takeoff, and the structure will fail completely. That final stress cycle is about to happen. At 2:59 p.m. Central Daylight Time, the control tower clears American Airlines Flight 191 to begin taxiing. Captain Lux acknowledges the clearance, and the aircraft begins to move, pushed back from the gate by a tug, engine started, beginning the journey from gate to runway. The taxi route is straightforward, across various taxiways toward runway 32 right. The DC-10 moves ponderously, its weight evident in every turn. Ground crews guiding it with hand signals and radio calls, other aircraft holding their positions to let it pass. The pilots go through their taxi checklist, verifying that flight controls move correctly, that instruments are reading properly, that systems are configured for takeoff. First Officer Dillard calls out the items. Captain Lux confirms them. Flight Engineer Udovich monitors his panel. Everything is routine, mechanical, practiced. They've done this thousands of times. The aircraft reaches the approach end of runway 32 right and holds short, waiting for takeoff clearance. Other aircraft land on parallel runways, their landing gear squealing as tires contact concrete, thrust reversers deploying with their distinctive roar. Controllers in the tower manage the sequence, spacing departures appropriately, ensuring separation between aircraft. At 3:02 p.m., the controller's voice comes through the pilot's headsets. American 191, runway 32 right, cleared for takeoff. Captain Lux responds. American 191, underway. The formality of the exchange, the professional tone, the standard phraseology, all of it speaks to a system that works, that has evolved over decades to be as safe as possible, that has protocols for everything. But no protocol exists for what's about to happen, because what's about to happen has never happened before in commercial aviation history. The DC-10 rolls onto the runway, lining up on the center line, that painted stripe stretching straight ahead for nearly 2 miles. First Officer Dillard, as the pilot flying, has his hands on the control yoke, his feet on the rudder pedals. He advances the 3 throttle levers smoothly forward, bringing all 3 engines up to takeoff thrust. Behind him, Flight Engineer Udovich watches his instruments, confirming that engine parameters are normal, N1 rotation speeds climbing, exhaust gas temperatures rising, fuel flow increasing. The engines reach their target thrust settings, each producing about 40,000 pounds of force, pushing the 165-ton aircraft forward with increasing speed. The acceleration is smooth, steady, relentless. The DC-10 gathers speed down the runway, 40 knots, 60 knots, 80 knots. The rumble of wheels on concrete filling the cabin, passengers feeling that familiar pressure pushing them back into their seats. At 100 knots, Captain Lux calls V1, indicating that the aircraft has reached the decision speed, the speed beyond which takeoff must continue even if an engine fails, because there's insufficient runway remaining to
stop safely. First Officer Dillard's hands remain on the throttles, committed now, no going back. At about 139 knots, roughly 160 miles per hour, with the aircraft about 6,000 feet down the runway, something happens in the vicinity of the left engine. A maintenance supervisor in a vehicle waiting to cross the runway, positioned to the side, sees it happen. Sees the left engine pylon begin to move, to shift, to separate from the wing. The cracked aft bulkhead has finally failed completely under the enormous loads of takeoff thrust. With that failure, the pylon's attachment to the wing becomes unstable. The engine, still producing full thrust, begins to rotate upward and aft around the forward attachment point, which becomes the only thing still holding the pylon to the wing. The rotation continues, accelerating, and then the forward attachment also fails, unable to handle the abnormal loads. The entire engine and pylon assembly, 6,400 pounds of metal, 40,000 pounds of thrust still being produced, separates from the wing. The sequence happens in perhaps 1 or 2 seconds, though it must seem longer to the maintenance supervisor watching. The engine and pylon assembly flips up and back, rotating over the top of the wing, trailing fuel and hydraulic fluid, tearing through the leading edge of the wing, ripping away a 3-foot section of the wing's forward edge, severing hydraulic lines and electrical cables that run along the front spar. The assembly then falls away, tumbling onto the runway behind the aircraft, bouncing and sliding and coming to rest on the concrete, still intact, but hopelessly damaged. A plume of white vapor or smoke, probably vaporized fuel or hydraulic fluid, trails from the wounded wing. The entire separation sequence is captured in photographs by Michael Laughlin,
a 24-year-old student pilot who happens to be at O'Hare with a camera photographing aircraft. His images will become iconic, showing the DC-10 with the left engine missing, the aircraft climbing, the moment frozen in film. Inside the cockpit, the pilots feel and hear the separation, a thump, a change in the aircraft's sound and vibration. First Officer Dillard's voice, captured on the cockpit voice recorder, says just one word: "Damn." A mild expletive, almost understated given the circumstances, but it's the last word the CVR records, because the left engine, which has just separated, was powering the cockpit voice recorder. With the engine gone, the CVR loses power and stops recording. The pilots still have partial awareness of what's happened. They know they've lost the left engine, though they may not realize the entire engine and pylon have physically departed the aircraft. The instruments on the first officer's side continue to function normally, powered by the remaining two engines. But the instruments on the captain's side have lost power, including several critical systems. The aircraft has passed V1, is past the decision speed, so the only option is to continue the takeoff. This is standard procedure, drilled into pilots in training. After V1, you're committed. You continue to get the aircraft airborne. You don't try to stop on the remaining runway. Captain Lux and First Officer Dillard follow this procedure perfectly. At approximately 6,000 feet down the runway, with the aircraft now traveling at about 145 knots, First Officer Dillard pulls back on the control yoke to rotate the aircraft, lifting the nose wheel off the runway. The main landing gear follows seconds later, and Flight 191 becomes airborne. For a moment, it must seem like the emergency is manageable. Yes, they've lost an engine, but DC-10s are certified to fly on two engines. The aircraft is climbing. They're airborne. They've cleared the worst part, the takeoff roll where they had no options. Now they have altitude, they have speed, they have time to assess and respond. But what the pilots don't know, what they have no way of knowing, is that the engine separation has done far more damage than simply removing thrust from the left side. When the engine and pylon tore through the wing's leading edge, they severed hydraulic lines. The DC-10 has 3 independent hydraulic systems, and normally this redundancy provides protection. If one system fails, the other 2 can compensate. But the routing of hydraulic lines on the DC-10 places several critical lines close together along the wing's leading edge, and the engine separation has damaged multiple systems simultaneously. Specifically, hydraulic system number 1 has lost pressure completely, and hydraulic system 3 has been damaged and is losing fluid, though it continues to function temporarily. The loss of hydraulic pressure has an immediate and catastrophic consequence. The DC-10's leading edge slats, movable surfaces on the front of the wing that extend during takeoff and landing to increase lift at low speeds, are held in their extended position by hydraulic pressure. On most aircraft, there's a mechanical locking system that keeps slats extended even if hydraulic pressure is lost. But the DC-10, as designed, relies entirely on hydraulic pressure to keep the slats extended. With hydraulic system 1 failed and system 3 failing, the slats on the left wing outboard of the engine position, the slats that were behind the now missing engine, lose their hydraulic pressure. With nothing holding them, with aerodynamic forces pushing against them, they begin to retract. Within seconds, all the outboard slats on the left wing have fully retracted, pulled back into the wing, leaving that section of wing in its cruise configuration, while the rest of the wing remains in takeoff configuration. This asymmetric slat condition creates an insidious problem. The left wing, with its outboard slats retracted, has a significantly higher stall speed than the right wing, which still has all its slats extended. A wing stalls when the angle of attack, The angle between
The wing's chord line and the relative wind exceeds a critical value, causing airflow over the wing to separate and lift to decrease dramatically. With slats extended, the DC-10's wings can handle angles of attack up to about 15 or 16 degrees before stalling. With slats retracted, the stall angle drops to perhaps 10 or 11 degrees. Flight 191's left wing now has a stall angle about 5 degrees lower than its right wing. At the aircraft's current speed and configuration, the left wing is perhaps 35 knots, 40 miles per hour, slower than its stall speed. But as the aircraft climbs and slows according to engine-out procedures, that margin will evaporate rapidly. The other consequence of the engine separation is electrical. The left engine drives an electrical generator, and with the engine gone, that generator is offline. This loss affects several systems that draw power from the number 1 electrical bus. Among the systems affected, the captain's flight instruments, which means Captain Lux has lost his primary attitude indicator, airspeed indicator, and altimeter. The slat disagreement warning system, which would have alerted the crew that the slats have retracted asymmetrically. The captain's stick shaker, a device that violently shakes the control yoke to warn of an impending stall. There's a backup power switch that could restore power to these systems, but it's not part of the takeoff emergency procedure, and the flight engineer would need to unbuckle, stand up, and reach across the cockpit to activate it. Not something that would typically happen in the first seconds after an engine failure. Additionally, First Officer Dillard's side of the cockpit doesn't have a stick shaker at all. American Airlines, in a cost-saving measure that McDonnell Douglas accommodated, had opted not to install stick shakers on the first officer side, believing that the captain's stick shaker was sufficient. So the situation is this. Flight 191 is airborne, climbing away from runway 32 right, with the left engine and pylon completely separated, hydraulic systems damaged, multiple electrical systems offline, the left wing's outboard slats retracted, creating a dangerous asymmetry, and no warning systems available to alert the crew to any of this. The pilots know they've lost the left engine. They see the engine instruments showing 0 thrust on the left. They feel the asymmetric thrust, the yaw to the left as the right engine produces thrust and the left produces none. First Officer Dillard applies right rudder to counteract the yaw, keeping the aircraft's nose pointed in the proper direction. He follows the standard engine-out procedure that's been drilled into him through years of training. Maintain directional control. Ensure positive climb. Accelerate to V2, the takeoff safety speed designed to provide adequate performance with one engine out, and then maintain that speed while climbing. The aircraft reaches approximately 300 feet above ground level, perhaps 20 seconds after liftoff. Everything seems controllable. The DC-10 is climbing, wings level, nose up at about 14 degrees pitch angle. First Officer Dillard has the aircraft under control, despite the asymmetric thrust. The 2 operating engines are producing sufficient power. American Airlines procedures call for the crew to reduce to V2 speed after an engine failure, and Dillard begins to slow the aircraft from its current speed toward V2, which is calculated to be about 159 knots. This is standard procedure, what every airline teaches, what the DC-10 flight manual specifies. The logic is sound. V2 is the speed that provides the best climb performance with one engine inoperative. Flying faster than V2 means you're not climbing as efficiently as you could be. Flying slower than V2 risks getting too close to stall speed. But V2 is calculated based on certain assumptions. The primary assumption is that only thrust is lost when an engine fails, that the engine stops producing power but remains attached to the aircraft, that the wing's aerodynamic characteristics remain unchanged, that all slats remain properly extended. V2 does not account for a scenario where an engine physically departs the aircraft, taking part of the wing with it, severing hydraulic and electrical systems, causing slat asymmetry. No one has ever imagined this scenario because it's never happened before. The certification requirements don't test for it. The training doesn't cover it. The procedures don't account for it. As the aircraft slows from its climb speed toward V2, passing through 170 knots, then 165 knots, the situation becomes critical. The left wing, with its higher stall speed due to the retracted slats, begins to approach its stall angle. The aircraft's pitch attitude is 14 degrees nose up. The bank angle starts to increase to the left, slowly at first. 1 degree, then 2 degrees, as the left wing starts to lose lift relative to the right wing. First Officer Dillard applies aileron input to keep the wings level, but the roll continues, accelerating. 3 degrees left bank, 4 degrees, 5 degrees. The aircraft is still climbing, but rolling increasingly to the left. The air traffic controller in the tower sees the aircraft's unusual attitude and radios, "Do you want to come back?" There's no response. The crew is too busy trying to understand what's happening, trying to control the aircraft. At about 325 feet altitude, approximately 31 seconds after liftoff, the left wing fully stalls. The airflow over the top of the wing separates completely. Lift collapses, and the wing effectively stops flying. The right wing continues to produce lift normally, creating a massive roll moment. The aircraft banks left rapidly now, the roll rate accelerating to about 4 degrees per second. 10 degrees left bank, 20 degrees, 30 degrees. First Officer Dillard applies full right aileron, trying to stop the roll, but the controls are ineffective against the asymmetric lift. 40 degrees, 50 degrees, 60 degrees. The aircraft's nose starts to drop as the stalled left wing loses lift. The pitch attitude decreases from 14 degrees nose up to 10 degrees, then 5 degrees, then level, then nose down. 70 degrees left bank, 80 degrees, 90 degrees. The aircraft is now flying on its side, wings perpendicular to the ground, still moving forward but starting to descend. Captain Lux and First Officer Dillard are doing everything they can, everything their training has taught them. But they're fighting physics and aerodynamics with insufficient information and insufficient tools. They don't know the slats have retracted. They don't know the left wing has stalled. They don't have stall warnings because those systems have no power. All they know is that the aircraft is rolling uncontrollably to the left, despite full control inputs to the right. 100 degrees bank angle, the aircraft rolling past vertical, now inverted. The left wing dropping, the nose dropping. 110 degrees, 112 degrees, the maximum bank angle the aircraft achieves. The ground is visible through the top of the windscreen now as the aircraft rolls inverted. The nose drops further, 30 degrees nose down, pointing at the ground. The aircraft is about 1 mile from the end of the runway, over mostly open ground northwest of O'Hare. Below is an area that includes a former airport called Ravenswood Airport, long since closed, its hangars abandoned or converted to other uses. There's an old storage hangar, some mobile homes in a small trailer park, warehouses and industrial buildings, open fields. The DC-10, now descending rapidly in its inverted attitude, has no more altitude to trade, no more options. The pilots pull back on the controls, trying to raise the nose, trying to arrest the descent. But the aircraft doesn't respond. The left wing is still stalled, the controls still ineffective. The aircraft impacts the ground at approximately 325 miles per hour, left wing and nose first, in a field at the intersection of what's now Touhy Avenue and Mount Prospect Road, on the border between Des Plaines and Mount Prospect. The impact is catastrophic and instantaneous. The aircraft is carrying nearly full fuel tanks, 21,000 gallons of Jet A, roughly 60 tons of kerosene, and the impact ruptures these tanks immediately. The kinetic energy of a 165-ton object hitting the ground at 325 miles per hour is beyond human comprehension, equivalent to perhaps 100 tons of TNT. The aircraft disintegrates on impact, breaking into thousands of pieces, none larger than a car, except for the engines and tail section. The fuel ignites, creating a massive fireball that rises hundreds of feet into the air, visible for miles. The explosion sounds like a bomb, rattling windows, shaking the ground, sending a column of black smoke into the perfect blue sky. The impact site is about 4,600 feet from the end of runway 32. Right, less than a mile from where the aircraft first rotated. Large pieces of debris are thrown forward by the force of the impact, hurled across the field, into the trailer park, into the old hangar. 5 mobile homes are destroyed, 4 from impact with debris and 1 from fire. 2 people on the ground, workers at a small auto repair facility near the impact point, are killed instantly by flying debris. Several other people nearby are injured, some severely. The fireball engulfs everything at the impact site. No one at the center of the impact has any chance of survival. All 258 passengers and all 13 crew members aboard Flight 191 are killed instantly. The total death toll is 273 people, making this the deadliest aviation accident in United States history, a record that still stands decades later. Emergency vehicles begin responding within seconds. Firefighters from O'Hare's Airport Fire Department, who saw the crash from the airport, race toward the site with their specialized crash trucks. Fire departments from Des Plaines, Mount Prospect, Chicago, and surrounding communities converge on the scene. Police, ambulances, emergency medical teams all descend on the crash site. But there's nothing they can do for the people aboard the aircraft. The heat from the burning fuel is so intense that firefighters can't approach for nearly an hour. When they finally get the fire under control and begin searching through the wreckage, they find no survivors, no intact bodies, nothing but burned and scattered remains. The scene is described by first responders as beyond anything they've experienced, worse than anything they've trained for. Some will need counseling for PTSD. Some will quit emergency services. Some will have nightmares for years. The news spreads quickly, first through emergency radio channels, then to news outlets, then across the country and world. Television stations interrupt regular programming with special reports. Radio stations break into their music and talk shows with bulletins. By evening, the crash is the lead story on every network news broadcast. The Chicago Tribune will later describe May 25, 1979 as the day Chicago stood still. At O'Hare, operations continue. The airport can't close, can't stop. Too much depends on it. But there's a somber atmosphere. Ground crews and gate agents and pilots and flight attendants all aware that 273 people died just a mile away. American Airlines begins the grim task of notifying families, of confirming passenger lists, of dealing with the horror of explaining to people that their loved ones aren't coming home. The investigation begins immediately, as it always does. The National Transportation Safety Board, the NTSB, America's aviation safety agency, is notified within minutes. An investigative team is assembled and dispatched to Chicago that same afternoon. By evening, NTSB investigators are at the crash site, beginning the meticulous process of documenting everything. The scene is secured as much as possible,
given the ongoing firefighting efforts. Nothing is moved until it's photographed and its position recorded. Investigators work through the night by floodlight, mapping the debris field, identifying major components, searching for the flight recorders. The cockpit voice recorder is found relatively quickly, its bright orange casing visible among the debris. But when investigators download its data, they discover that it stopped recording just after First Officer Dillard said, "Damn," when the left engine separated. The last 20 to 30 seconds of the flight, the critical moments when the aircraft rolled and crashed, are not recorded. This is unusual and immediately suggests that the engine separation somehow affected the CVR's power supply. The flight data recorder is also recovered and provides more useful information. Its data shows the engine parameters, the aircraft's speed and altitude and bank angle, the control inputs, a wealth of information that will prove crucial to understanding what happened. But even before the flight recorders are analyzed, the physical evidence tells a clear story to trained investigators. The left engine and pylon, lying on runway 32 right where they fell, are obviously separated from the aircraft. This alone is extraordinary. Engines don't just fall off aircraft during takeoff. Investigators examine the pylon attachment points and quickly identify the critical failure. The aft bulkhead of the pylon has fractured completely. Close examination reveals that the fracture surface has characteristics of both fatigue cracking and overstress failure. Part of the bulkhead failed due to a crack that grew over time, and the rest failed suddenly when the remaining structure could no longer
Carry the load. Within days, the investigation focuses on maintenance procedures. Inspectors from the NTSB traveled to American Airlines maintenance facility in Tulsa, Oklahoma, where N110AA had undergone its last major maintenance 2 months earlier. What they find there shocks them. American Airlines has been removing and reinstalling DC-10 engine and pylon assemblies as single units, using a large forklift to support the combined weight of the engine and pylon while mechanics disconnect the mounting points. This procedure is not approved by McDonnell Douglas, not described in the maintenance manual, not the procedure that the aircraft manufacturer recommends. McDonnell Douglas had specifically advised that engines should be removed from the pylon first, then the pylon removed from the wing separately, to avoid placing abnormal loads on the pylon structure. But American Airlines engineers had developed the single-unit procedure to save time and labor. Removing the engine and pylon separately required about 200 man-hours per engine. Removing them together cut that time significantly, perhaps by 60 or 70 hours, and also reduced the number of connections that needed to be disconnected and reconnected. Hydraulic lines, fuel lines, electrical cables, control linkages, from 79 to 27. Fewer connections meant fewer opportunities for errors, or so the thinking went. The procedure had been developed carefully, evaluated, tested on several aircraft, and had been used successfully multiple times. Other airlines, including Continental Airlines and United Airlines, had developed similar procedures using either forklifts or overhead hoists. But the procedure was inherently difficult to execute properly. The forklift operator couldn't see the actual attachment points where the pylon connected to the wing. Those were above and behind the forklift, out of the operator's line of sight. The operator had to rely on hand signals and radio communications from mechanics positioned where they could see the attachments. The pylon and engine assembly, weighing about 6,400 pounds, needed to be positioned with millimeter precision to avoid contacting the wing structure during removal or reinstallation. Any misalignment, any shift in the forklift's position, any settling of the forklift's hydraulics could cause the pylon to contact the wing in ways that would damage the structure. Investigators interview the mechanics who worked on N110AA in March 1979. They learn that during the reinstallation of the left engine and pylon assembly, there were difficulties. The work began on one shift and continued on to the next shift after a change of personnel. At some point during the reinstallation, the pylon appeared to bind or jam against something. The forklift had to be repositioned. Mechanics reported hearing unusual sounds, possibly the sound of metal contacting metal, but attributed them to normal work noises. No one realized that the pylon's aft bulkhead had contacted the wing clevis, a U-shaped fitting on the wing that the pylon attaches to, with enough force to crack the bulkhead. The crack was internal, inside the structure, not visible from the outside. After the reinstallation was completed, mechanics conducted the required inspections. But those inspections didn't involve disassembling the pylon to look for internal cracks. The aircraft was returned to service with a damaged pylon, a ticking time bomb that would fail after a few more weeks of operation. The NTSB orders an immediate inspection of all DC-10s in the American Airlines fleet, and then expands the order to all DC-10s operated by U.S. carriers. Investigators find alarming results. In the American Airlines fleet, they discover 3 more DC-10s with cracked pylon aft bulkheads, damage identical to what caused the Flight 191 crash. Continental Airlines, which had also been using the forklift procedure, has 2 aircraft with similar cracks. In both Continental cases, mechanics had heard sounds like gunshots when the cracks occurred, but had attributed them to other causes and hadn't reported the incidents to McDonnell Douglas or the FAA. One Continental DC-10 has an engine that can be rocked back and forth by hand because the pylon structure is so compromised. In total, investigators find 6 DC-10s with damage to the pylon aft bulkheads, and all 6 cases involve the use of the unapproved forklift procedure. The implications are staggering. Multiple airlines had independently developed similar procedures, all based on the reasonable goal of saving time and labor, none approved by the manufacturer, all capable of causing catastrophic structural damage. The FAA, which is responsible for overseeing airline maintenance, had not detected these unapproved procedures or prevented their use. McDonnell Douglas had not been informed about the damage incidents at Continental. There had been a complete breakdown in communication and oversight, with potentially disastrous consequences. That Flight 191 was the first fatality was almost luck. Any of the other damaged aircraft could have suffered the same failure, possibly with the same result. On June 6, 1979, less than 2 weeks after the crash, FAA Administrator Langhorne Bond takes unprecedented action. He issues an emergency order of suspension, immediately grounding every DC-10 in the United States and prohibiting any DC-10 from entering U.S. airspace. This is the first time the FAA has ever grounded an entire aircraft type, and it sends shockwaves through the aviation industry. A total of 138 DC-10s registered in the United States are grounded, along with dozens more operated by foreign airlines. Airlines scramble to accommodate passengers using other aircraft types. Some routes can't be flown at all without the DC-10s. The financial impact on airlines is enormous. But the FAA has no choice. Until the cause of the crash is fully understood and corrective actions implemented, no DC-10 can be considered safe to fly. The grounding lasts 5 weeks. During that time, every DC-10 in the world undergoes intensive inspections. Pylon attach points are examined using specialized techniques, including ultrasonic testing that can detect internal cracks. McDonnell Douglas issues revised service bulletins specifying exactly how engine and pylon maintenance must be performed, prohibiting the forklift procedure. requiring that engines be removed from pylons before pylons are removed from wings. The FAA mandates these procedures, making them legally required rather than merely recommended. Additionally, McDonnell Douglas develops modifications to the DC-10's systems to address some of the vulnerabilities revealed by the accident. The leading-edge slat system is modified to include a mechanical locking mechanism that will keep slats extended even if hydraulic pressure is lost, providing a backup similar to what exists on other aircraft types. The stall warning system is modified to draw power from multiple sources rather than just the number one engine, ensuring that stall warnings will function even if one engine is lost. The flight crew procedure for engine failures is revised to specify that if an engine fails after V2 speed has been reached, the crew should maintain whatever speed they have rather than decelerating to V2, providing a safety margin against the scenario that befell Flight 191. On July 13, 1979, after extensive inspections and modifications, the FAA lifts the DC-10 grounding order. The aircraft returns to service, but its reputation has been severely damaged. Public confidence in the DC-10, already shaken by the 1974 Turkish Airlines cargo door accident, is now at an all-time low. Many passengers specifically request not to be booked on DC-10 flights. Some airlines quietly retire their DC-10 fleets earlier than planned. The aircraft becomes known in some circles as the death cruiser, an unfair characterization, but one that reflects public perception. Sales of new DC-10s slow dramatically. McDonnell Douglas struggles to compete with Boeing's 747 and the emerging Boeing 767. The NTSB issues its final report on Flight 191 on December 21, 1979, 7 months after the crash. The report is exhaustive, running to hundreds of pages with detailed technical appendices. The probable cause is stated clearly. The asymmetrical stall and the ensuing roll of the aircraft because of the uncommanded retraction of the left-wing outboard leading-edge slats and the loss of stall warning and slat disagreement indication systems resulting from maintenance-induced damage leading to the separation of the number one engine and pylon assembly at a critical point during takeoff. The separation resulted from damage by improper maintenance procedures which led to failure of the pylon structure. But the report doesn't stop with identifying American Airlines' maintenance procedure as the primary cause. It also identifies numerous contributing factors that created the conditions for disaster. The vulnerability of the pylon attach design to maintenance damage. The structure had very little tolerance for misalignment or abnormal loads. The vulnerability of the slat system design, which relied entirely on hydraulic pressure, with no mechanical locks as backup. The routing of hydraulic lines along the wing leading edge, where they were susceptible to damage from an engine separation. The lack of redundancy in power supplies for critical warning systems. The deficiencies in FAA surveillance that failed to detect the unapproved maintenance procedures. The lack of communication among airlines, McDonnell Douglas, and the FAA about maintenance incidents and damage. The inadequacy of training and procedures for a scenario that had never been contemplated. Massive structural failure during takeoff. The report makes dozens of recommendations, many of which are implemented quickly. The FAA revises its regulations governing maintenance procedures, requiring that any deviation from manufacturer-approved procedures be formally reviewed and approved. Airlines are required to report all maintenance incidents that result in structural damage, even if the damage is repaired, so that patterns can be identified. Certification requirements for new aircraft are enhanced to require analysis of failure modes that could result from maintenance errors, not just in-flight failures.
McDonnell Douglas and other manufacturers improve their maintenance manuals to provide clearer guidance and warnings about procedures that could cause damage.
American Airlines is fined $500,000 for using improper maintenance procedures, a significant sum in 1979, equivalent to millions today. Continental Airlines receives a fine of $100,000 for similar violations. But the largest cost is not financial, it's human. The families of the 273 victims file lawsuits seeking damages, and many of these cases take years to resolve. The emotional toll on families, friends, colleagues, and the broader community is incalculable. Memorial services are held. Names are read aloud. 30 of the victims cannot be identified from remains and are buried together in a group memorial. American Airlines creates a memorial fund. The cities of Des Plaines and Chicago honor the victims. In October 2011, more than 3 decades after the crash, a permanent memorial is dedicated at a site near where Flight 191 impacted. The memorial consists of a decorative garden bordered by a brick wall, and in that wall are embedded 273 bricks, each engraved with the name of one person who died that day. The memorial is located in Lake Park in Des Plaines, on a quiet street near the crash site, which has long since been cleared and redeveloped. Families visit, especially on the anniversary of the crash. They leave flowers, stand in quiet reflection, touch the names. For many, this is the only grave their loved ones have, the only place where they can come to remember and grieve. The memorial is simple, dignified, respectful. 3 qualities that feel appropriate for commemorating lives cut so suddenly short. The DC-10 itself would go on to have a long career, despite the reputational damage from Flight 191 and other accidents. The last DC-10 passenger flight operated in 2014. In total, about 446 DC-10s were built, and they flew safely for millions of hours, carrying hundreds of millions of passengers, proving themselves capable and reliable once the known issues were addressed. The aircraft became particularly popular as a freighter, and FedEx operated a large fleet of DC-10 cargo planes for decades. The DC-10's successor, the MD-11, improved on the design, but never achieved the same sales success, in part because the DC-10's reputation overshadowed its derivative. Today, a few DC-10s still fly in cargo service, their distinctive 3-engine configuration still recognizable to aviation enthusiasts. The lessons from Flight 191 rippled through the aviation industry in ways both visible and invisible. The most visible change was the immediate modification of DC-10 slat systems and warning systems, preventing any similar accident on that aircraft type. But the deeper lessons were about systems, about assumptions, about the importance of communication. The accident revealed that maintenance procedures could be just as critical to safety as design features, that cost and time savings had to be balanced against risks, that informal modifications to procedures needed oversight and approval. It revealed that redundancy in aircraft systems needed to account for damage scenarios, not just simple component failures. It revealed that incident reporting and information sharing among airlines needed improvement. The NTSB's investigation also pioneered new techniques for accident reconstruction. Investigators used computer simulations extensively for the first time, recreating the flight in simulators to test theories about what happened and what the crew experienced. They put test pilots in simulators configured to match Flight 191's conditions. With the left engine failed, the left slats retracted, no stall warnings available, and asked them to save the aircraft. Not one of the 13 test pilots succeeded. Every simulated flight ended in a crash. This definitively demonstrated that the crew of Flight 191 had been in an unrecoverable situation.
that no amount of skill or experience could have saved them, that they had done everything correctly according to their training and procedures. The accident wasn't pilot error. It was a systems failure, a design vulnerability, a maintenance procedure problem, an oversight failure, a communication breakdown. It was everything except the crew's fault. This finding brought some measure of closure to the families of Captain Lux, First Officer Dillard, and Flight Engineer Udovich, who could know with certainty that their loved ones had been professionals to the end, that they had fought to save the aircraft, that they had done nothing wrong. It also reinforced a principle that accident investigators have long understood, but that the public often struggles with. Most accidents result from chains of events, from multiple failures that align in improbable ways, from conditions that individually seem harmless but collectively create disaster. Flight 191 didn't crash because one person made one mistake. It crashed because a maintenance procedure seemed reasonable but had hidden risks, because a pylon design had minimal tolerance for misalignment, because a slat system lacked backup locks, because warning systems drew power from a single source, because procedures didn't account for unprecedented scenarios, because oversight didn't detect the issues, because information wasn't shared. Remove any one of these factors, and the accident likely doesn't happen. But all of them aligned. The holes in the Swiss cheese lined up perfectly, and 273 people died. Today, more than 4 decades after Flight 191, commercial aviation is immeasurably safer than it was in 1979. The accident rate has decreased by more than 90%. Fatal accidents in commercial aviation are now rare enough that each one dominates news cycles for weeks. In the United States, major airlines now operate with safety records measured in billions of passenger miles between fatalities. This improvement didn't happen by accident. It happened because accidents like Flight 191 were investigated exhaustively, because the lessons learned were implemented systematically, because the industry
Committed to learning from every failure. Flight 191's legacy lives on in every modern aircraft, in the redundancy designed into systems, in the procedures that govern maintenance, in the reporting requirements that ensure information is shared, in the training that prepares crews for scenarios that previous generations never imagined. It lives on in the families who lost loved ones, and who have worked to ensure their losses weren't in vain, who have supported aviation safety initiatives, who have kept the memory of that day alive. It lives on in the memorial at Lake Park, where 273 names are preserved in brick, where anyone can come to remember, to reflect, to pay respects. The story of Flight 191 is ultimately a story about the fragility of complex systems, about how the best intentions can lead to disaster when combined with incomplete understanding, about how safety requires constant vigilance and learning and improvement. It's a story about 273 people who boarded an aircraft on a beautiful Friday afternoon, expecting nothing more than a routine flight to Los Angeles. People with plans and dreams and families waiting for them. People who trusted the aircraft and the airline and the system to bring them safely to their destination. That trust was betrayed, not by malice or incompetence, but by the subtle accumulation of small decisions and design choices and procedural adaptations that together created a vulnerability no one had recognized. In the years since the accident, investigators, engineers, regulators, and airline personnel have worked tirelessly to ensure that the specific failure mode that destroyed Flight 191 can never happen again. The forklift procedure has been banned. Pylon attach points have been strengthened and better designed. Slat systems include mechanical locks. Warning systems have redundant power sources. Maintenance procedures require formal approval. Incident reporting is mandatory. Every DC-10 that still flies,
and every aircraft that came after benefits from these improvements. Flight 191 taught the industry lessons that have saved countless lives. And while that's small comfort to those who lost loved ones that day, it's the only meaning that can be drawn from tragedy, that others might be spared similar fates because of what was learned. As you lie here tonight, drifting toward sleep, think about those 273 people whose names are preserved on a memorial wall in Des Plaines. Think about Captain Lux and First Officer Dillard and Flight Engineer Udovich, professionals who did everything right, but faced a situation no training could have prepared them for. Think about the flight attendants who never had a chance to evacuate passengers, about the passengers who never arrived at their destinations, about the families forever changed by a single Friday afternoon in May. Think about the invisible work that goes into every flight you take. The maintenance procedures followed precisely, the inspections conducted meticulously, the redundancy built into systems, the lessons learned from every accident and incident that came before. Think about how commercial aviation has become one of the safest forms of transportation precisely because the industry learns from its failures. Because accidents are investigated not to assign blame, but to prevent recurrence. Because safety is a continuous process of improvement rather than a final destination. The investigation is complete. The memorial stands. The lessons endure. And commercial aviation, that most audacious of human endeavors, continues its long march toward ever greater safety. One flight at a time, one lesson at a time, one improvement at a time. Carrying millions of people safely across vast distances, connecting families and cultures and opportunities, making the world smaller and more accessible, all built on a foundation of knowledge paid for by those who came before. The cockpit voice recorder has been silent for more than 40 years now, stopped in mid-word as power failed, preserving forever that moment when everything changed. The flight data recorder has told its story, its thousands of data points analyzed and understood, revealing the physics and mechanics of the accident. The wreckage has long since been removed, the crash site redeveloped, the runway where the engine fell repaired and returned to service. But the memory remains, preserved in official reports and memorial walls and family stories. A reminder of both the vulnerabilities in complex systems and the human cost when those vulnerabilities are exploited by circumstances. Good night, and may all your flights be safe ones. May the lessons of the past protect the travelers of the future. May the names on that memorial wall in Des Plaines be remembered not just as victims, but as the people they were, loved, missed, honored, and never forgotten.